Welcome to the 95th Theoretical-Physics-Colloquium by Piotr Surowka from Warsaw University of Science and Technology in Poland. He received his PhD in 2010 at Jagiellonian University in Poland. He had several postdoctoral positions afterwards, first at Freie University in Brussels and International Solar Institute between 2010 and 13. Then he spent 3 years at Harvard University between 2013 and 16. And since 2016, he was a research associate in Max Planck Institute, Munich, and then worked also as a staff scientist in Dresden, also at Max Planck Institute. Since 2021, he is an associate professor in Wrocław University of Science and Technology. He has a wide research interests ranging from many-body physics to high-energy physics. He worked on quantum anomalies in hydrodynamics, hydrodynamics from charged black brains, transport in holographic superfluids, quantum materials, graphene, Dirac and Weil semimetals, active matter and metamaterials, chiral metamaterials. And today he will be talking about odd viscoelasticity. And with that, I'll give the microphone to Piotr.
Okay, so first of all, let me thank Igor for inviting me to to give this colloquium. I understand the audience is mostly coming from the high energy angle, so I try to be quite pedagogical and try to bring viscoelasticity to high energy physicists. So do not hesitate to ask any questions if anything is not clear. And with that, I will start by some motivation why we should be interested in studying viscoelasticity. And since the audience is mostly interested in astrophysics, let me say that one of the applications of viscoelasticity in that context is to neutron stars. And neutron stars are collapsed massive stars that are very dense. They're almost as heavy as black holes. And what is important that to model appropriate properties of neutron stars is actually important to take into account both elasticity, because the crust is elastic, but at the same time the core of the neutron star is more like a fluid. So if we want to have a joint low energy effective theory of a neutron star, it should be viscoelastic. On top of that, there are some ideas that maybe anomalies can be important in this context also, which means that parity symmetry is broken, and then that naturally leads to the conclusion that we should develop some kind of chiral version of viscoelasticity. Another more condensed matter-oriented application of viscoelasticity that is actually physics of quantum. Viscoelasticity is important there. So we know that quantum Hall states are very strongly coupled systems. So in some sense, maybe the most strongly coupled systems, interactions are very relevant. And then it's not so easy to describe them using first principles. So people come up with different phenomenological and pictorial, let's say, ways to understand quantum Hall states. And one of such ideas is actually that there is a gapped mode in the context of quantum Hall systems that is called magnetoroton. And Haldane proposed that this magnetoroton mode is described by a dynamical object that has two indices. And then this idea was further explored more like phenomenologically by Tokatui and later by Son, and they realized that the hydrodynamic description of these quantum Hall states is not only like a fluid, but actually it's a viscoelastic medium. And then like more, let's say, engineering oriented application is in the context of composite metamaterials. So what are composite materials? One basic example that we probably know from everyday life is, for example, concrete that combines properties of steel that is hard and heavy with just like pure concrete that is relatively light and cheap, and together they form reinforced concrete that is used widely for constructions, because then it's like relatively light, cheap, and quite strong. On top of that, nowadays engineers and applied oriented physicists can construct materials that are built from some like robotic ingredients and program these ingredients to have like desired features. And then if we program these robots in a way that they rotate or they break chirality and include some energy losses due to dissipation, then it naturally leads to the conclusion that a proper description is in terms of viscoelastic solids. So developing viscoelasticity can potentially describe some exotic metamaterials made out of these robotic chiral objects. Okay, and something that is also like a field that is quite vibrant and emerging recently is the so-called active matter, and that's heavily inspired by biology. Basically, it describes large scales of systems that are built of something that can consume energy and can move. So of course, in biology, it's like very natural to have systems that consume energy at some like basic microscopic scale, for example, flock of birds, or like a fish or a school of fishes. And then as we expect, there might be some like low energy description for some for these systems that is more hydrodynamic in nature. And then it turns out that viscoelasticity is precisely a framework that can capture some of the key features of these systems, and in some sense it generalizes let's say what we know from equilibrium passive systems, because then new structures or new transport coefficients can appear that are due to the intrinsic activity that is there in the system. And then just to give you, let's say, a picture behind this active matter business. So roughly as in hydrodynamics, we have classes of systems parameterized by momentum conservation. So if a system doesn't have doesn't conserve momentum, then we call it a dry active matter. And if the system is more like a fluid, in the sense that then we classify it as wet active matter. And as I said before, we are interested in systems like herds or like flocks of animals. So this would be active systems. And to name an example of wet active matter, we can have some like bacteria moving in some viscous fluid, and then it's more like a viscous suspension or a viscoelastic suspension, and that would be more like a momentum conserving system that is here classified as wet. Okay, so with this like quite general introduction where viscoelasticity can be applied, let me just go to the more like technical details, like physics details. So let me start with the Landau paradigm and follow the exposure of Zhang and Wen. So Landau paradigm states that we can classify states of matter by symmetry principles, and then that means that if some symmetry is broken, then we go from one phase to some other phase. Like at the level of like pictures, we can have some system with the potential, and then if there is a degenerate space of this potential, the potentials that leads to forces the system to spontaneously break the symmetry, and then pick up one of these potentials. And this is applied to like many systems. There can be, for example, spins that are randomly distributed, and then we cool them down, and then doesn't have any particular structure, but then we go to like lower temperatures and a solid structure develops, which means that atoms now take some specific positions in strain. So our initial continuous symmetry is now broken. And then if we are interested in having more precise description of this mechanism, then we should develop the theory of elasticity in its like basic incarnation, so that people did a few hundreds years ago, and that starts by saying, okay, since our atoms, let's say, start picking a special position, we can describe that by a field that is like a field that captures the positions, and then if we coarse grain the system, that field becomes continuous and basically tells us about fluctuations around some equilibrium positions of the atoms. And as I told you, this corresponds to a symmetry breaking, which means that this field is more like a phase, and only the gradients somehow are important. So if we now are to find like the distances in our initial and deformed solid, we can expand to the leading order, and that gives like a basic incarnation of elasticity by the so-called strain tensor, that is a symmetrized tensor of the gradients of elastic fields. Now, this is not the end of the story, because we can have like more general elastic theories. So one way would be to go to like next order, so develop nonlinear theories of elasticity. But another thing is we can say that our material has some intrinsic structure. So it's not only like atoms, but let's say our solid is made out of some small cells with structures and dimensions. And in this case, we can try to include that scale in the system. And one, let's say, consistent way to do it is the so-called Viscoelasticity, that apart from this displacement field introduces the orientation of that cell, and then deforming the solid would distort both the displacement and the initial rotation of the cell. And then we have to modify our theory and include that rotation as some angular variable. So here I presented how it works for the free energy. So if we impose both translation and rotation symmetry, then the gradients of displacement fields are not invariant, but we can construct this gamma, which is a combination of a gradient and the rotation field. And using that, we can build the free energy again as an expansion. So that's then known as Viscoelasticity. And then how to include viscous effect to that elastic picture. So let me give you like a basic exposure of hydrodynamics that contains effects due to viscosity by starting with diffusion. So the diffusion can be thought as like a minimal example of hydrodynamics when the momentum in our system is not conserved. Then we can simply write down the diffusion equation in the form of some density field and a gradient of a current, and then supplement that with some constitutive equation. So if we now expand this current as a function of chemical potential, that is the thermodynamic conjugate to density, then we can rewrite everything in terms of densities and some like free parameters, and we get precisely the diffusion equation. So one novelty here, if we have systems like active matter in mind, is that this D is not constrained in a similar way as for passive diffusion. So it can be both like positive and negative. So physically, it means that, you know, if you have just diffusion, the atoms in the initial position will just like spread. But of course, if there is something like consuming energy microscopically, it can as well happen that they will just go back to the initial position, and then the diffusion coefficient will not obey the same constraints as in the passive case. Okay, now we can think how to include momentum conservation, and this is done in a similar manner. So probably for this audience, we take momentum equation on top of the conservation of density. We expand the stress tensor that is a current for momentum as a derivative expansion, and then add, let's say, energy or entropy conservation to that, and play a bit and get Euler's equation in the as an ideal equation for the fluid evolution. If you go to higher gradients, it's very easy to include dissipation in the system. Now, our goal somehow is to combine these two features, like having both like elastic responses and viscous responses, and this can be done actually like quite easily, having some like one-dimensional pictures. And I think the original ideas are quite old. Like Maxwell developed a lot one-dimensional viscoelastic models. And that's basically amounts of connecting springs and the so-called dashpots or dampers. So then if we have a spring, we know that the response will be elastic. So if we look at the stress-strain relationship, if we stretch the spring, there will be some initial strain. If we stop stressing, it will go back to the initial position. On the other hand, if we stress the dashpot, it will just linearly expand. And if we neglect some like physical limitations, how long the tube is, the strain-stress relation is more or less like linear. So as long as we stress, we have strain. If we stop stressing the system, we just stop doing anything. Then if we try to construct strain-stress relationship for many, let's say, everyday life materials, we'll have something that is neither elastic nor viscous. So we have to somehow combine the two to get like more complicated diagrams. Okay, so here is just the summary of what I said at the level of equation. We can write down the constitutive equation. So let's say we have strain on the left-hand side and stress on the right-hand side. For the spring, there is just the spring constant that connects them, and that's the usual elastic behavior that we discussed before. That's why it's quite natural to model solids as some kind of springs that connect atoms. On the other hand, if we want to write down the constitutive equation for the dashpot, it looks more like a fluid constitutive equation. So now there is no like stress-strain relation, but now the gradient of strain is related to stress by some coefficient that we can identify as shear viscosity. And then we can write the equation, we can solve them, and then from that we can determine the diagram and the relations between stress and strain. So the quantity that captures that is the so-called creep compliance function. So we basically try to determine what is the time behavior of the strain given some stress. So as I told you, for fluids and dashpots, this relation is like linear in time and is controlled by viscosity, and for springs and elasticity is just constant and it's captured in 1D by an elastic coefficient. Now we can try to think how to combine the two. And again, a pictorial representation is like very nice, but now there are more possibilities. So we can, if we have one spring and one dashpot, we can connect them in parallel or in series. So let me start by showing you what happens if we connect them in parallel. If we do that, we can write down the constitutive equations for springs and for the spring and the dashpot, and say that the total stress is equal to the sum of the stresses of the constituents. And then if we solve the equations for sigma 1 and sigma 2 and get rid of them, we can write down one constitutive equation that relates strain and stress. And you see that now it contains both the elastic and the viscous part, and we can solve it. The solution gives you a natural parameter which is called the retardation time, and this time is just the ratio of viscosity and the elastic coefficient. And it captures how much time it takes for the creep strain to accumulate in the material. Now let's think what happens if we connect the spring and the dashboard in the series. So now instead of stresses, we can say that the strain now is the sum of the strain on the dashboard and strain on the spring. Again, we can solve the equations and get a simple constitutive equation that now has a new feature that stress becomes like a variable. So it will later become quite important in constructing like more complicated models, because now we cannot easily write down equation for the stress in terms of strain and plug it back to the other equations, but we have to treat stress as a dynamical variable in our hydrodynamic formulation. Again, we can solve the equations and get a modified form of the strain dynamics, which now contains this linear in time behavior, but there is also this offset by the elastic part. And here are the strain-stress relation of the Maxwell and Kelvin-Moy model. So in the Maxwell model, you have some initial jump and then linear in time behavior, and in the Kelvin-Moy it's more like a smooth function. Okay, so now we could say, great, we are more or less done. We have constructed like viscoelastic models, and that's it. And actually, for a long time, that's what people had, and they were quite happy about it. But unfortunately, it doesn't give you an agreement with like experimental measures of responses, especially for more complicated materials like polymers or some biological tissues. So we have to do something else. We have to modify these models to make them a little bit more complicated. And first we have to identify which features do we want to correct. And here is a list of these features. So for example, the Maxwell model predicts creep, but the creep does not decrease with time. So that's not something that we observe. On the other hand, the Kelvin-Voigt model doesn't have any like stress relaxation. So if we have a solid with a stress relaxation, it's beyond Kelvin-Voigt. Also, the equations are not covariant. I will tell you in which sense. There is no chirality in these systems. So if we are to describe, let's say, viscoelastic theory of some chiral neutron stars, it's not enough to have just this simple incarnation of viscoelasticity, even though like people applied probably this to extract some knowledge about like neutron stars. And then there is no plasticity. Okay, so how can we go beyond these simple models? One idea is, let's take more springs or more dashboards. And then again, this is what people have tried. There is a vast literature about these models. If we have 2 springs and 1 dashboard, these are the so-called standard linear solids, or like Zener models. You can again play this game with, like, writing down initial, like, individual stresses and strain, combine them, and try to establish the constitutive equations for the whole circuit, both for the solids and the fluids. So now the fluid is something that contains, like, let's say 2 dashboards and 1 spring. And then, as you see, we have, like, more parameters, so some relaxation time or retardation time, and some dynamics in both stresses and strains. So that's, let's say, one direction in which we can go to correct our models. Another thing that we can do is try to have more, like, first principles, symmetry-based approach to viscoelasticity. And before I tell you how to do that, let me go back to the Navier-Stokes equations. So let me take Galilean invariant fluid for simplicity, although it is not necessary to do so. And then we can say that the fluid should respect Galilean invariance. So we write down time, position, velocity, and see how do they transform under Galilean transformations. And then one can check that, for example, the gradient field is invariant, the velocity field is invariant, but unfortunately, the time derivative invariant with respect to Galilean transformation. So then, by, let's say, playing a bit, we can try to see what combination is invariant, and then we recover this combination between time derivative and the projection of gradient and velocity field, and this is known as the material derivative. So if we combine the two, we just get again Euler's equation, and then if we add viscosity, we get Navier-Stokes equation modulo some unidentified function that we say it's pressure. Now we would like to generalize this this philosophy to, like, viscoelastic system, and that again was done quite some time ago, but not, let's say, in the modern formulation. So at the beginning of 50s, Oldroyd, who was after, like, viscoelastic models of fluid, tried to construct, let's say, covariant time derivatives with respect to, now we would say, like, diffeomorphism symmetries, but at the time it was just symmetries of like frame changes. And then I think by playing and guessing, he constructed, like, some derivatives, which now we can formalize and say basically he constructed, like, a Lie derivative for tensor fields. And this is important because I tell you, if we have stress, then stress is a two-index object. So if we want to have a time derivative that acts on the stress and transform covariantly, it is natural to say that the proper derivative is a Lie derivative with respect to the fluid particle velocity. So then, this symmetry principle basically allows one to write viscoelastic models that I presented in one dimensions, in higher dimensions, in like covariant manner. So now let me go back to the chiral part of the story. Now we have a viscoelastic theory that is covariant, that let's say in principle can contain all these more complicated stress-strain relationship. And the question is, how can chirality enter into the game? So again, let's go back to the constitutive equation. So we can expand the stress tensor, let's say in higher dimension in a similar manner as we did in 1D. And now the coefficients will be just 4-index tensorial quantities that will be fixed by symmetries. So for the parity even case, K and eta will just contain the usual Lamé coefficients and shear and bulk viscosities. However, as we know, if parity is broken, then in principle more terms are allowed. And then let me just tell you how this works like in 2D. That is like the simplest example. And then if we had isotropy and parity broken in 2 dimensions, then our viscosity tensor can contain an antisymmetric pieces. And then this antisymmetric piece we can show at least in the simplest formulation, it can be without dissipation. And we can do that by study, for example, entropy production. So if we do that, then T times time derivative of the entropy will be just our viscosity that is constructed with time derivatives of the strain tensor. So because Uij dot is symmetric, then the antisymmetric part of the viscosity tensor drops out automatically. And that means that entropy is, in this setup is not generated by this antisymmetric contribution. And now we can ask a question, what is this antisymmetric contribution? And by now, it's like pretty well established, and in 2 dimensions is known as odd or whole viscosity. And there is just one coefficient and can be expanded in like the tensor can be expanded in delta functions and epsilons, and then this combination has the right mathematical properties. But let's now try to get some more intuition what this whole viscosity does for you. So in the usual case, let's say you have a blob of some material immersed in a fluid. If we start rotating, there is some like shear force that will try to counteract this act of rotation, and that leads to shear response. Now whole viscosity is different. It gives you like perpendicular response. So if you try to rotate your object, in principle the force now will be perpendicular to the initial direction of motion. And this is why it cannot, it cannot contribute to dissipation. Now, let me just mention that odd viscosity does not need to be only realized in passive system. There are these ideas by Devu Banerjee, Anton Suslov, Sasha Abanov, and Vincenzo Vitelli that constructed a hydrodynamic model for a bunch of like spinning objects that are, as I told you, quite popular in the field of active matter or like metamaterials. And then what they showed is if we take a rotating ensemble of chiral objects and expand around some non-equilibrium rotating state, effectively this also contributes a term that is similar to odd viscosity, controlled by this angular momentum variable. So, you know, by now it's known that odd viscosity is not only a non-dissipative coefficient, but it can also exist in like dissipative incarnation, and you know, in this sense, it can describe some active systems. Now the question is, can something similar as odd viscosity exist in elasticity? And naively, we would say no. It's a textbook knowledge that the elastic tensor has certain symmetries known as like minor symmetries that exchange between the first and second pair of indices, and the so-called major symmetry that exchanges these pairs, the first and second pair indices together. And that means that antisymmetric part cannot be there, at least not in the passive incarnation. However, let's say we don't care about like constraints coming from like passivity. We can try to formulate the most general two-dimensional, let's say, for the sake of simplicity, model of elasticity that is isotropic, but we do not require energy conservation. So there is a very neat representation due to Avron in terms of Pauli matrices of two-dimensional elasticity. The tensor, the elastic tensor, is now a 4x4 matrix, and then we would like to fix the entries by imposing isotropy and see what conducts the energy conservation. And what happens that is that in the passive case we have just two entries that are left if we impose the symmetries, and these are the two Lamé coefficients. However, if we do not impose energy conservation, we can have two more coefficients. So the coefficient A will come due to rotations. However, there is this one coefficient that is called here kappa 0, and that's a coefficient that is like analogous to odd viscosity, and we dubbed it as odd elasticity. And then here is some possible mechanical realization of that odd elasticity. So you take some springs that are now active themselves, so they can respond with some torques, and in principle, if we construct like a network of that, of these springs, we should get this like quite exotic odd elastic response. So in the last steps, let me just show you that the there is a similar construction that can be applied to fluids. It's slightly more complicated, but again, we can take the constitutive equation of, let's say, two-dimensional viscoelastic hydrodynamics that would be of this form, and then say that we do not require our system to be even under parity symmetry. That means that in principle, this eta and kappa inverses would contain this odd viscosity or odd viscosity and odd elasticity in the active incarnation. And then we study the properties of that. There is like one physical mechanism that is quite unique to odd viscoelasticity in a fluid, and basically it couples compression with rotation. So usually this cannot be. Compression decouples completely from rotations. However, here, due to these odd coefficients, there is some cross-coupling between them. And then one comment is that if I focus purely on the non-dissipative part, I recovered what Son recently constructed to study fractional quantum Hall states, and he called it chiral metric hydrodynamics. So like this non-dissipative chiral metric hydrodynamics is what I would call odd viscoelastic Maxwell fluid. And then to close, let me just say that we are now thinking how to probe these odd coefficients and odd properties in usual materials. And one idea that we developed recently is the emergence of an odd lift force. So let me just remind you briefly what a lift force is. So if you go to the airport and board the plane, you try to take off, then the lift force is crucial, and it comes usually because the airfoil, or like the wing of our plane, is modeled in such a way that the air fluid flows faster on top of the wing and slower at the bottom, and that creates a pressure difference between the bottom of the wing and the top of the wing that results in some perpendicular force called the lift force that allows plane to fly. Now we can ask a similar question in the context of like odd fluids, and in the simplest incarnation it would be like a disk that is embedded in an odd fluid, and try to see if there is a lift force. Now it turns out that if we impose incompressible approximation, as shown by Ganeshan and Abanov, the lift force is vanishing, and even in the compressible scenario, it's not easy to get an odd lift force. It requires some mass that is slightly broken. However, one can also show that actually an odd lift force emerges if now we have some time dependence in the system. So let's say we take our cylinder or our object to oscillate, then the lift force will be proportional to some non-dimensionalized omega tilde, which is non-dimensionalized oscillation frequency times the logarithm of that frequency. So then, in principle, this opens up a possibility to measure odd properties of materials using that phenomenon. So, as a summary, let me say that the take-home message is, odd viscoelastic fluids are characterized by this coupling between compression and rotation. And then if we try to probe it by some external bodies embedded in the fluid, if there is some time dependence in the system, we should be able to get some non-zero lift out of the odd coefficients that are there. So this is more or less like one application to the non-relativistic cases. We haven't studied yet what happens in the relativistic case. That would be maybe more suitable to astrophysics or like nuclear physics applications. We haven't included yet external fields. We didn't look much at curve background, so I think there is a lot to do in this field, and I hope you will also become interested. So thank you.
Thank you very much for a nice presentation. Now we will have some time for questions. So if you have a question, please raise your hand and we'll proceed with that. I don't see any questions from the audience yet, so let me start by breaking the ice first. You mentioned about the possibility of this viscoelastic fluid realization in the quantum Hall effect, fractional quantum Hall effect, yes. The work by Son. I was a little bit confused about that statement because apparently during the derivation, you were assuming that the energy conservation is broken. My understanding is that in the quantum Hall effect, there is no breaking of the energy conservation. So isn't there some kind of contradiction there, or am I missing something?
To be more precise. So what I told you is that we start with this general set of viscoelastic equations for a fluid. Now, in principle, eta and kappa are not fixed by some general principles, but you have to look at specific properties of your system. So in the quantum Hall physics, you have to get rid of the shear viscosity in the vision, and it's a quantum system, but you can. And then in the kappa tensor, you can get rid of odd elasticity, but you can still leave passive elastic coefficients. So if you do that, then you recover the model of Son that conserves energy, and there is nothing active about it. But there is this oddity that is manifested through the odd viscosity, and there is an equation for the evolution of the stress that characterizes a viscoelastic medium.
So essentially, I guess my confusion started earlier, and I think you might have answered that. So basically, there is no odd elasticity, only odd viscosity. Is that what you're saying? Because the reason I asked, because if you go back maybe 1 or 2 pages, you were talking about this odd elasticity. And that's where you said that the only way to get those extra coefficients is to assume that the energy conservation is broken. Right here, the bottom matrix.
Yes, at least in the Kelvin void model. At least in the Kelvin void model. So that's important that you cannot have passive odd elasticity in the simplest incarnation setups. But what happens is that usually in this case, you have some like strong dissipation that just leads to a suppression of this mechanism. But of course, if you have like quantum systems, probably you cannot, or like patients, you probably cannot have odd elasticity, but you might still have odd viscosity that is there.
I see. Okay.
And then of course, this is only like two-dimensional. So we haven't touched like 3 dimensions. If you, let's say, go to like Weyl semimetals and then introduce external magnetic fields, you know, that requires like a detailed study, like which coefficients are allowed. Then you break like background fields, but still there might be some like also viscoelastic regimes that you know, are far richer than what people like considered in the past.
I see. Okay, we have another question from Henry de Jong. So do you want to ask it yourself or should I read it on your behalf? Go ahead.
I can ask it.
Go ahead.
Thank you very much for a very interesting talk, especially in regards to understanding perhaps in better MEMS devices and so on and so forth. One question I have is, have you looked at this analysis in regards to neutron star mergers and like determining equation of state and so forth?
No, like I haven't touched like future on my list of things to do, but yeah, that would require probably some like interdisciplinary effort to, you know, combine knowledge between, let's say, nuclear or like neutron star practitioners and you know, people interested in viscoelasticity. But it's a very, very interesting direction, I would say. And if really like viscoelastic modeling is important for neutron star, and you know, it seems it is, then maybe to account correctly for all associated phenomena, one just has to do it carefully.
Right. Okay.
Thank you.
Any other questions from the audience? At some point when you were discussing this odd viscosity, I think at first, you were basically saying that you drop the parity as one of the symmetries, and then of course a lot of additional options open up. Now, I don't remember you mentioned anything about time reversal symmetry. Are there any additional things, or you automatically break time reversal? If you break time reversal, are there any additional constructions or response that might still enrich the possibilities?
So I would say that by construction, like viscoelasticity breaks time reversal, because at least in this active framework that I presented to you, because then you have like in a sense, like viscoelasticity is a transient phenomenon. You start in like with some non-equilibrium scenario, and then you flow either towards like equilibrium or to an equilibrium liquid. So in this sense, like the time reversal is like always broken.
Well, the fact that there is something dissipationless, and that's when you have something like that, doesn't necessarily mean that you have time reversal symmetry broken, does it?
No, in the context of quantum Hall, probably not. So that's why I'm talking. What I told you was mostly like focus on the active systems.
Mm-hmm.
Something more in the quantum systems. I'm not sure, but I don't think there is, because I think, at least in the context that Son studied, he somehow wrote down like the most general thing allowed by symmetries. So he didn't write down anything else. So I don't think there is anything, at least for his class of quantum Hall states. Maybe, if you have some other class of states in mind, that could be, but I don't know. Like, that's something to be studied.
Fair enough. Fair enough. Any other questions? I don't see any raised hands. So
I have some question here.
Go ahead, please.
Okay. It's personal reason, man. My son is coming chemistry, always looks at birds outside. Red or blue, anything. My question to who talks about in physics, it doesn't matter. He talks about birds, the birds always on the black.
So, sorry, I didn't catch the question.
Yeah. When my son talks to birds here with the colors here, but the part is first on the departments here to the birds action here doesn't matter if all are on the black. I mean, chemistry.
So, I mean, I use like birds as motivation. So
right.
Probably here there is not much about like birds per se. So
okay. Okay, now we'll see. Okay, easier. It's a model here. Okay.
Yeah. So like usually like flocks of birds are modeled by a set of equations called like Toner-2 equations, and they have a different form than this like viscoelastic system. So, I mean, a message I try to convey is that there is a wide spectrum of active matter systems in which you not only want to like maybe understand nature, but to some extent also like create physical phenomena. And some of these systems will be described by viscoelastic models. And I presented one of the models that should be applicable to like viscoelastic fluid with some chiral constituents and category.
Okay.
I don't know if that answers your question, because.
Okay. Anyway, I just wanted to use this moment to first thank you for a nice presentation.